Good afternoon, everybody. Welcome to lecture. Today we're going to continue our discussion of oxidizing agents and oxidation reactions. These are reactions that take carbon and increase its oxidation state, give it more bonds to oxygen or fewer bonds to hydrogen, or both. And before we get into that, though, I want to do this survey question that appeared in your assignments list, and this is one that asks you to rank the following alkenes according to their heats of hydrogenation. And there's 1, 2, 3, 4 examples of alkenes here. And I peeked at the statistics, and the statistics were sort of mixed. In other words, a lot of people got it right, but a lot of people got it wrong. And I want to make sure that we clarify this, and it's really crystal clear why the order is the way that it is. First of all, the important thing to remember is that if an alkene is high in energy, it gives off a lot of energy when it reduces and goes down to an alkane. So if you've got a very unstable alkene, it'll give off a lot of heat. So less stable alkene means more heat. More stable alkene means less heat. So that might not be immediately like intuitive, but once you think about it for a while, hopefully you can wrap your head around that and get used to it. So really what this question boils down to is it's asking us to order the stabilities of these alkenes, and then the one that's the least stable gives off the most heat, and the one that's the most stable gives off the least heat, and then all the ones in between are in between. So let's recall what it is that makes an alkene stable versus another. There are two factors, the most important of which is substitution. What you want to do is look at the alkene, the carbon-carbon double bond, and ask yourself how many carbon groups are attached to that carbon-carbon double bond. The more carbon groups that are attached to the alkene C double bond C, the more stable it will be. If we look at this list of structures here, we have a tri-substituted alkene here. The C double bond C has 3 alkyl groups on it. That's a very high degree of substitution. Then we've got a disubstituted alkene here and a disubstituted alkene here. Those two are less highly substituted, so they'd be less stable. And then finally over here we have a monosubstituted alkene. This is a carbon-carbon double bond that has just 1 R group attached. So this would be the least stable. So that's factor number 1. Then if you have a tie like we do here between the two disubstituteds, you look to steric strain to try to break the tie. The steric strain in molecule 3 is going to be a lot higher because it's a cis alkene, and the methyl group and this isopropyl group are going to be in each other's space. So it's going to create some strain that's going to tend to make this one higher in energy than the trans. So now we can order them in order of stability. Least stable is number 4, then number 3, then number 1, then number 2. And that's the order of the energy that we're going to get out for hydrogenation. The least stable, number 4, gives off the most heat. So that's going to be a 4 is going to be generate the most heat. Then the next least stable one is the cis disubstituted alkene. That's going to give a little less heat. 1, the disubstituted trans will give off less heat, and then the trisubstituted will give off even less heat. So the correct answer here is C. So, yes.
Number 2, what happens if you take off the ethyl group?
Okay, so the question is on structure 2, imagine we removed the ethyl group, and then we'd have a disubstituted geminal. Yeah, okay, so disubstituted geminals come somewhere between cis and trans. So the ordering among disubstituted alkenes is trans is the most stable, followed by geminal disubstituted. That's when you have a carbon-carbon double bond that has 2 groups on 1 carbon and just H's on the other carbon. And then the least stable alkene, disubstituted alkene, is still the cis. So that's a good question. So in this case, C is the correct answer. And if you got a different answer, just see what the problem was. Was it with your understanding of orders of stabilities of the alkenes, or was it with the fact that less stable alkene gives off more heat? Just kind of square your understanding with the results, and then you can keep getting the right answer each time you get one of these. And I know for sure there's one in the questions in the homework assignment for the lecture, and there's probably going to be one on the exam. It could very well be one on the exam. So work on that concept. All right, speaking of the exam, exam 1 is coming up on Monday, the 29th of September. So let's go take a look at Canvas, and I want to share with you the page or the module for exam 1 that has a page in it that gives a lot of information about exam 1. You can get to this by navigating to the home page and scrolling down to almost the bottom, and you'll see there's a module for Exam 1 info, and I'll click on the Exam 1 info page. So Exam 1 is going to be given in lecture on Monday the 29th, right here in this room, unless you've got other arrangements. It's going to cover material that was described in the syllabus. You're going to get a bunch of reference materials. You can bring and use a calculator and a plastic model kit. You can't bring any notes. And then calculators need to have nothing stored in the memory. As long as it's not a fancy calculator that's like a tablet or a phone or something, it'll work fine. The only reason you might want a calculator is to do some addition and subtraction for mass spec fragments. I think that's probably the only application that you really have. You won't need it to do a lot of complicated ratios on NMR signals, because I'm not going to ask that kind of question. I'll give you integration information that you can use, and the ratios will be simple enough that you can just, shouldn't need a calculator to solve them and figure out the ratios of protons, but you can bring a calculator if you want. You're going to be given a bunch of reference material, and all of this stuff these are all references that we've talked about or discussed in class. You're going to get tables of spectral data. You're going to get a table of IR frequencies, mass spec common fragments, proton NMR, and carbon NMR chemical shifts. These are the packets that we've been working with and that are posted in Canvas that you've probably been studying with, and you'll have those available. You're also going to get a list of oxidizing and reducing agents from Chapter 12. It's the same list that we've been talking about for the last few lectures. You're going to get a nomenclature reference sheet, which you probably won't need, but it's there just in case you want to look at it. You'll get a pKa table and a periodic table, and all of those things you can use as needed. There will be molecules of the day on this exam. So the molecules of the day are these molecules that I talk about once in a while at the start of lecture, and I've got a list of them here now. I populated this table with the molecules of the day that we've seen so far, and I've introduced a new one as well. So you might remember cinnamaldehyde, cucumber aldehyde, cetirizine, and then this new one. This is our new molecule of the day, which, by the way, is really complicated looking. I'm going to blow it up, but it's a really exciting molecule, so don't worry, you don't need to memorize it. In fact, if you want to just remember this is the complicated one, that would probably work. It's the other one that I'm going to introduce on Friday won't be nearly this complicated. But look at the elaborate nature of the structure here. There are nitrogens. This is a really nitrogen-dense molecule. It has many nitrogens, it has 2 fluorines, it's got some oxygens in it, it has numerous stereogenic centers. It's a really complicated looking molecule. And the reason it's interesting is that it's right now, the name of this thing is, and I'm going to try to pronounce this as best I can, or froglipron is, I don't know if that's exactly correct, but it is the name that we have so far. This is a molecule that's in phase 3 clinical trials as a new obesity drug. You probably heard in the news a lot about Ozempic and Wegovy. these are the ones that make the news. They are currently in use. This is a newer generation drug that promises to potentially be better, and phase 3 clinical trials means it's progressed really pretty far. From what I read, it's going well. And the thing that's unique about this one is it's an organic small molecule, whereas the others, the previous generation molecules, are peptides, which are also organic molecules, but they're held together by amide bonds, and we're going to talk about that later in the semester. The problem with peptide drugs is that they don't last very long in the body, and they generally have to be administered by injection. This is one that is a pill. So people take this as a pill. Way better delivery method, and apparently the thought is it's going to be a lot cheaper so it could be a blockbuster drug. This molecule might be worth billions of dollars in the near future. I mean, multiple billions. And that's the molecule of the day today. So this molecule, that's obesity drug. This is really cutting edge stuff. It's not a drug yet, it's in clinical trials. But you may see advertisements in the years to come. It's going to have some brand name, but then you'll see this like in small font off to the side or something when the commercial comes on and tries to advertise that, if it passes through all of its hurdles on the way to becoming a drug. So that's molecule of the day. I have one more for you Friday. It's going to be simpler. It's going to be a pretty small little molecule, but a fun one. Any questions about the exam? All right. Well, let's continue on then and discuss the oxidation reactions that we left off with last time. Last time we were talking about epoxidations, and we're going to continue on with that theme, and we'll discuss how they work. So epoxidation of alkenes is a reaction that we talked about last time. Here is generally how it works, and I'm going to show you a mechanism that explains this. I'm going to lower this down so I have lots of room up here. This is a reaction of a peroxy acid and an alkene. The peroxy acid has this structure. The R group on a peroxy acid can be many different things. We've seen the MCPBA structure that has a benzene ring with a chlorine on it. We've seen a methyl group, and there are others as well. But they all behave in basically the same way. This molecule likes to adopt this conformation where the oxygen and this oxygen and that hydrogen form a hydrogen bond intermolecularly, which means within the same molecule. So it holds it in this 5-membered ring conformation. And when it approaches the alkene, that oxygen right there is the one that gets close to the alkene, and then it forms a transition state where there's like a triangle that's going to form. And those dotted lines that I'm listing right there are going to indicate that's where new bonds are going to form. And there's a series of electrons that move. And I think what I'm going to do here is also put in the lone pairs on the oxygen here. I'll put them in on the oxygen here and on the oxygen here. Okay, so here's how the movement works. And this is not a sequential movement. It's like all the electron pairs are going to move at once. But we're going to draw arrows to indicate where they're going and where they're ending up. So I'm going to start an arrow at the alkene pi bond, and I'm going to show it going to the oxygen of the peroxy acid right there. Then there's a bond that breaks, and it's going to be this weak oxygen-oxygen single bond. And that's going to be the driving force for the reaction, is going to be breaking that weak bond and replacing it by a stronger bond. The electrons in that oxygen-oxygen bond are going to shift this way to make a new oxygen-carbon double bond there. When that happens, we have to move some electrons away from this carbon because it's already got 4 bonds, and if you form a new one to it, an old one has to go. And that's what this one is going to do. This pi bond here is going to move to make a new bond to that hydrogen. So we're going to get a new bond between this oxygen and that hydrogen. The electrons in the hydrogen-oxygen bond are going to go to oxygen. And then this oxygen, one of the lone pairs on the oxygen can bite back on the carbon, the other carbon, to make another carbon-oxygen bond. Okay, it's a lot of arrows, I realize, but let's take a look at what we get when we're done. It looks pretty weird, huh? Well, here's your consolation, is you won't have to reproduce this mechanism or draw these arrows on an exam. It's just it's a little too much. But it's interesting, I think, to know how it works. And when you see the product up here, maybe it helps you make sense of everything. So this is an epoxide down here. That's the functional group of interest, the thing that we did the reaction for. This is a plain old carboxylic acid. A vanilla garden variety carboxylic acid, not anything unusual. This was a peroxy acid, which was the new type of really reactive species, peroxy acid. So there you go. You get a three-membered ring where there used to be a carbon-carbon double bond. All right, let's go and talk about prediction of products with this. There is some stereochemical consequences of how this works that are important. The O approaches the alkene from one of its two faces, and that approach means that there's going to be a certain product distribution, and we're going to talk about that over here on the next board. An important note about this, cis alkenes give cis epoxides. And transalkenes give trans epoxides. Let me show you what I mean. We'll tackle the cis example first. If you start with a cis alkene, like say for example, cis 2-butene, and you put in a peroxy acid, like I will say this one, you get on an epoxide. The epoxide is going to have cis stereochemistry. The two methyl groups here are on the same side of that dotted line that bisects the double bond. They're going to be pointing in the same direction in the epoxide in the product. So the epoxide product will have the three-membered ring, and the two methyl groups will be pointing in the same direction. CH3 on a wedge bond, CH3 on a wedge bond. So cis alkene leads to cis epoxide. Now there are two faces that the peroxy acid can approach. This is one of the two possible products. The other one, the other face of the alkene, if the other face got attacked, if the peroxy acid approached from the other direction, there would be this product. I'm going to probably slide this over a little bit so it doesn't get quite so smushed. So hydrogens on wedges and methyl groups on dashes, but it's a cis epoxide in both cases. The thing is that this molecule has a mirror plane of symmetry that runs through the middle of it, this one and that one. So it turns out these end up being the same molecule in this case. This isn't always true, but in this example, these molecules are the same. If you took this one and you flipped it over, you could lay it exactly on top of that one and you'd have the same molecule. That doesn't always work for cis alkenes, just symmetrical cis alkenes where the two groups on either side are exactly the same. Yeah, there's a question. It is okay, yeah. The question was, do you need to write in the hydrogens on an exam? No, you don't. As long as you have, if you showed methyl on a wedge, and left out the hydrogens on a dash, that's implied that they're there. And I know that you know that they're on a dash, so that is okay. I think for Alex, I think it can usually identify when they're not there, it's okay with it. So different computers have different rules about that, but yeah, as long as it's clear, then and that would be clear. Putting just the methyl groups in and leaving out the hydrogens, that'd be okay. That's a good question. Now let's take a look at what happens if you do a trans. If you do a transalkene, and I'll do, for simplicity, I'll use the same 2-methylbutene, but I'm going to use trans 2-methylbutene, and I'll put in the same peroxy acid. We get a trans epoxide. The epoxide comes in the oxygen, adds to the 2 carbons of the alkene. And in this product, there's the trans methyl up and methyl down over here, but there's this other product as well. The other possibility is that the left methyl is down and the right methyl group is up. And this is just determined by which of the 2 faces the epoxide or the peroxy acid approaches when it attacks. Does it attack from the top face here that's closest to you or from the behind face? And these 2 are not the same. These 2 are actually different. These are a pair of enantiomers. So they are 2 stereoisomers, and the question may ask you to draw both. I'm pretty sure the homework has questions like this where it'll give you an alkene and you have to decide, is there one stereoisomers, yes or no, and if there are, you should draw them both. Okay. Any questions about this epoxide stuff? All right. Remember the one epoxide forming agent that is really, really common, I didn't write it here today, but it's this MCPBA molecule. I think what I'm going to do is give you another example of this just to get that molecule on the board one more time because it is so common. So here's an alkene, and you might see, for example, MCPBA, and then on an exam, I'd also give you the structure of MCPBA, maybe off on the side or something. I'd say the structure of this molecule is this. It has a benzene ring. It has this functional group, which is a peroxy acid, and then there's a chlorine up here. MCPBA. It stands for metachloroperoxybenzoic acid. Metachloroperoxybenzoic acid. All right. So we form an epoxide here. Our epoxide is going to have 2 methyl groups on one side and 2 hydrogens on the other side. This is a skeletal structure of the molecule. You could draw the methyls in if you want, but you don't have to. There is no stereochemistry associated with this product because there are no stereogenic centers. So this is one where you don't need dashes and wedges to describe it or a stereoisomer of it. That's good enough. And then if you were, asked about what's the other product, just in case, the other product is the benzoic acid that forms when the peroxy acid is done reacting. So this is the other product that's of less interest. So there's an example of a epoxide forming reaction with MCPBA.
Are they going to make us draw that on a test?
MCPBA, no.
Just like the second, like that?
No, I don't think, well, if you had this structure, then I think you could get to this one. So I think it'd be okay. It probably wouldn't be a type of problem that I'd like to emphasize that, because understanding the structure of the benzoic acid is important. This one's a little more complicated than most, though. So, I think it would be an okay question. I'm just not sure I'd want to invest time in having you draw it. So, all right. Well, that's epoxides and that formation, and that's one of the big oxidation reactions we have. Now, once you have an epoxide, you can do some things with it. And one of the next thing we're going to talk about is opening of epoxides by hydroxide. That's a strong base and a strong nucleophile, and it's a way to make something called a 1,2-diol. So the next thing in the chapter is talking about dihydroxylation type reactions. Dihydroxylation reactions to make syn and anti-diols. So what's a syn and what's an anti-diol? Let me show you. Here's a two-step process that you can do to make an anti-diol. If you put an alkene in with an epoxidizing agent like MCPBA, you'll get an epoxide out. And the epoxide can be drawn like this. So what I've done here is to put the oxygen poking out of the plane. I've got the 6-membered ring in the plane. I have the 2 H's on dashes, and I have the O on a wedge bond. Now, when you draw this in Alex, you can draw it like this, but just make sure that the fat parts of the wedges are on the oxygen, and the skinny parts, the thin parts, are on the carbons here. You could also draw the other version of this where you've got dash bonds to the oxygen and wedge bonds to the hydrogen, and that would also work. Just make sure that the fat part of the wedge or the dash bond is on the oxygen, and then Alex will recognize it as right. So that's epoxide formation. Now, if you put this in with water and hydroxide, hydroxide can attack and open the epoxide. And there's 2 places it can attack. It can attack either that carbon or that carbon. And in this molecule, they're both equally attractive. So I'm going to put partial positive charge here, partial positive charge here. And in the upper case, if it attacks here, this bond breaks, and you get an intermediate that looks like this, where there is an OH on a dash bond. And the reason I know that is that this is an SN2 substitution reaction, and there's inversion of configuration at the carbon that's being attacked. So this is an SN2 reaction, strong nucleophile attacking epoxide. So it comes in from the face opposite of where the leaving group is leaving from. So since the O is pointing on a wedge bond towards you, the nucleophile OH has to come in from the backside behind. So this gets delivered with a dash bond orientation, and then the H that's on a dash gets bent out of the plane and becomes on a wedge. So that's inversion of configuration at the carbon here that's being attacked. The carbon below isn't affected stereochemically because it's not participating in the SN2 reaction, so there's an O- here, and then there's an H. So that's one possible product. Then the other thing that could happen is the OH-, instead of attacking at the top carbon, could attack at the bottom carbon right here, and that bond could break. And then you get a version of the intermediate that has just alternate structure, where the OH is delivered on a dash bond orientation, but to the bottom carbon. And the H gets bent out onto a wedge. And then in the upper carbon, there's the O-. That gets produced when the epoxide opens. So these are two intermediates that you get. And then the last thing that happens in these reactions is the water provides a proton source for the O- that you generated. So there's a water molecule that gives a proton to this O-. So that happens, and then the final product is that you get a dialcohol, and I'll just draw it in here with the OHs to remove some of the clutter from the H's on the ring. That's a anti-diol. The other one that you get is if the bottom reaction occurs, then water provides a proton to that O- down here, and you get the following molecule. So these are both anti-diols. The reason they're anti is the OH groups got added to opposite faces of the carbon-carbon double bond. So if the OHs are pointing in opposite directions, that's an anti-diol, and this is the way to get it. This is the way to synthesize an anti-diol from an alkene, is first make an epoxide, do an epoxidation of an alkene to give you an epoxide, and then open it with hydroxide nucleophile. That is an anti-1,2-diol. All right, let's talk about syn dihydroxylation next. In addition to anti-diols, you can also make syn-diols, but the reagent that you use is going to be different. So these are going to be some new reagents that we're going to talk about, and there are two that are very similar. They do very similar jobs. So this is going to be about syn dihydroxylation of alkenes. And here is the overall reaction. I'll illustrate it with cyclohexene. You can use KMNO4, that's potassium permanganate, hydroxide and water, or you can use a two-step process that uses the reagents osmium tetroxide, and then in a second step, sodium bisulfite. These are two reagents that are described in the table that you've got of reagents. So we're just kind of working down the list in the table that I gave you to explain all the reactions that are happening. The product is going to be something called a syn-diol. So you get two hydroxyls. It's a dihydroxylation, but it gives the hydroxyls having their OH groups pointing in the same direction. So this is a syn-diol. It gets that name because the OH groups are added to the same face of the alkene. In this case, it's the top face. They can also add to the bottom face, in which case the OH groups would be dashed lines instead of wedged lines. But with this molecule, that's the same molecule because this molecule has a mirror plane of symmetry, and you just flip it over and then the OH groups are on dashed lines. So we'll see examples where we predict products in alkenes that are less symmetrical, and then you get a couple of stereoisomers. But for starters, I just want to introduce the two reagents. Then we can talk about the mechanism, like how does it work? How does this reagent and that reagent react with an alkene to produce this thing? So we'll do that over here. And the two mechanisms are very, very similar. So here's a mechanism for the potassium permanganate reaction. Alkene reacts with potassium permanganate, and here's what the permanganate molecule looks like. It has a couple of double bonds to oxygen, actually 3 double bonds to oxygen, and then an O- with a K+. This molecule is at a very high oxidation, that atom is at a very high oxidation state, and it really wants to unload some of its oxygens to get some electron density back. And the way that this works is that the electrons in the alkene react with the oxygens on the KMNO4, and here's how the electrons move. I'll start a pair of electrons moving at the alkene double bond, the pi bond, and I'm going to show them moving to make a bond to one of the 2 oxygens. I picked this top one. You could have also picked the bottom one, and the only difference then is the electrons would be shown going counterclockwise versus clockwise, but it's the same process. So you make a new bond between that carbon and that oxygen by moving a pair of electrons there. Then a pair of electrons goes into the manganese here, and then a pair of electrons in the oxygen-manganese double bond go to form a new bond to that carbon. So there's 3 pairs of electrons that move, and you get a molecule that's got a manganese incorporated into it. You get a ring, basically, that's got a manganese atom in the middle of it. This is sometimes called a manganate ester. That term isn't one you have to know, but the important thing is when this happens, this goes with syn addition. The O's add to the same face of the alkene. So the O's end up on wedges or dashes. The big thing is they point in the same direction. And then the less important, more complicated, less well-explained type step in the reaction is that there is a process whereby water and hydroxide react to cleave off the manganese. And so basically this part cleaves off and you end up with a syn-diol. And there's also, I should also probably draw a lone pair on the manganese at this point because it's got one. Don't worry about the fate of the manganese. It's actually pretty complicated what happens to it, but it gets washed away in a water layer. But you get a syn-diol is the big important thing here. And this is the mechanism for how it works with the potassium permanganate. Now, with osmium tetroxide, it's a pretty much identical or analogous reaction. I'm going to draw the osmium tetroxide here. The structure of that oxidant is very similar. It's got a couple of double bond oxygens in one direction and a couple double bond oxygens in the other direction. It's got a lot of bonds to oxygen. And it can line up with the alkene like that, and electrons can move in an analogous manner. A pair of electrons in the pi bond can go and attack one of the oxygens of the osmium tetroxide. A pair of electrons in that osmium oxygen double bond can go to osmium, and then a pair of electrons in the osmium oxygen double bond here go to make a new bond there. So you get something called an osmate ester, which is got a structure that's very analogous to the manganate ester that we drew a picture of up here. It has an osmium that's bonded to the carbon piece through these oxygens. And when it happens with a syn addition. The 2 oxygens end up pointing in the same direction. And then the other step, which is another one you're not going to have to know step by step how it works, but there needs to be treatment with some sort of reducing agent, and the reducing agent that gets used is sodium bisulfite. There's also 2 double bonds to oxygen that are still here. The osmium has a pair of electrons on it. But the result is the same. You get a syn diol. Just 2 different ways to get to the same thing. The reason it's nice to have 2 is this one is a little more selective, but it's way more expensive and it's really, really toxic. Osmium tetroxide is really scary toxic. It attacks the optic nerve, so this is one I don't ever want to work with. This one is reactive, but it's got a lot better toxicity profile. So a couple of different ways to do dihydroxylations and get syn diols. Let's take a look at a predict the product type question where essentially you're given an alkene and you got to figure out what might you get out of it. KMNO4, hydroxide water. When this alkene gets put in with this oxidizing agent, we're going to get a syn diol. Let's figure out how to draw that. The 2 OHs have to come in from the same face. So you can draw them coming in from the top face or from the bottom face, and both are going to be likely positive. They're both going to happen. So when we draw the product, we're going to need to get both of those products. So one of them has an OH group here up, OH group here up, and then the other product, which is the stereoisomer, forms when the reagent approaches from the other face of the alkene. But again, it's a syn diol in both cases. And you could replace osmium tetroxide and sodium bisulfite, 2-step process here, and you get the exact same product. So that's dihydroxylation. Any questions about that? All right, let's talk about oxidative cleavage of alkenes then. That's one of the next reactions in the list that we need to talk about. Oxidative cleavage of alkenes with ozone. That's O3. This is called ozonolysis. Ozonolysis. Ozone is a powerful molecule. It is produced in the upper atmosphere when sunlight hits oxygen, causes a reaction that generates ozone, and then it also absorbs UV light and protects us from UV rays. So up there it's great, but down here at ground level it's pretty toxic stuff and it's considered a serious pollutant because it's so reactive. Here's the structure of ozone. It's a little bit wild looking. I'm going to show an alkene and I'll show you ozone and then we'll talk about how it reacts. So ozone is O3. It has this structure. It's 3 oxygens bound together. One of them has a formal minus charge, one of them has a formal plus charge, and then one of them is neutral. And this is one of 2 possible resonance structures. The other resonance structure puts the minus charge on that oxygen, and then that one would be neutral. So overall, ozone has the end 2 oxygens having a minus a half a charge and the middle oxygen having a +1 charge. And there's no way to spread the electrons out evenly in this molecule due to the way that oxygen can't make more than 4, it can't have more than 8 electrons around it, so you can't simply share these electrons into that oxygen. It's stuck like this in this pretty unstable position or configuration. And when it sees an alkene, it approaches it like this. Does that look familiar? We're getting this 5-membered ring kind of transition state theme going on here. And this is one of the things about organic chemistry. When you start looking at a lot of mechanisms, they start to look similar. You start to see patterns that occur over and over again. And this is one of these recurring patterns. And I'm going to draw the mechanism here for how ozonolysis, the first step of ozonolysis works, and that the ozone lines itself up with the alkene, and then a pair of electrons in the pi bond go and make a new bond to that oxygen. A pair of electrons in the oxygen-oxygen double bond go to oxygen, and then a pair of electrons off this O-, they go and they make a new bond to that carbon, and you get a molecule that looks like this. It has 3 oxygens attached to it. These things are not very stable. This is a really unstable intermediate, and the reason is that it has a lot of these really high energy oxygen-oxygen single bonds that are very unstable, not very stable. It's a syn addition process, so I'll draw these methyl groups as having wedges. This changes, it rearranges to become a different molecule where there's an oxygen that ends up between, sort of slipping in between the carbons. This part of the mechanism you're really not required to know. It's just sort of for interest. And then what has to happen in the next step is that some other reagent is put in to act like a reducing agent that acts actually as a reducing agent, and that molecule that usually gets used, what you usually see is a molecule called dimethyl sulfide. So dimethyl sulfide is a sulfur that has 2 methyl groups on it, and then the sulfur has 2 lone pairs of electrons. And the purpose of this is that the electrons in the sulfur attack one of these oxygens and take it away. And the final product is you get 2 molecules of aldehyde or ketone. And then you also get a molecule of the dimethyl sulfide. The fate of the dimethyl sulfide is that it becomes a molecule called dimethyl sulfoxide. So if you're doing the stoichiometry and you look at where you started, you've got the 4 carbons and the 3 oxygens. In the products, we've got our 1, 2, 3, 4 carbons and our 1, 2, 3 oxygens. So everything is accounted for. So essentially, you need this reagent to mop up the 1 extra oxygen that comes with the ozone. So that's how it works. Let's look at some predict the products questions, because that actually ends up being the easier part of this. Predicting the products of ozonolysis reactions ends up being pretty easy when you learn a trick or two, and I'm going to show you the tricks. This is about predicting products of ozonolysis. What you want to do is draw your alkene. And I'm going to draw a generic alkene here where I'm going to put R groups labeled R1, R2 on the left carbon, and R3 and R4 on the right carbon. And these R groups could be hydrogens, they could be carbons, or any combination of those. But when you put this in with ozone, and the way the reaction is always going to be set up is there's going to be a step 1 where it's O3, and there's going to be a step 2 where you add that reagent and that dimethyl sulfide. And predict the products just do this. Imagine slicing the molecule in half like that. Literally break the two carbons apart, move them apart, and in place of the carbon-carbon double bond, give each carbon a new carbon-oxygen double bond. Let me walk over there and show you what I mean. I'm going to take the left carbon, and I'm going to put R1 and R2 on it, and then I'm going to give it a double bond to oxygen. Then I'm going to take the right carbon over here, and I'm going to give it the R3, R4 groups that it came with, and then I'm going to give it a carbon-oxygen double bond. So overall, the process is you start with an alkene, you break it in half, pull the pieces apart, and just cap the carbons off with oxygens to make double bonds, like that, carbon-oxygen double bond. If you can get that, it's really pretty easy. So let's look at some examples over here of predicting the products and using that strategy. So we'll use some real alkenes, and then we'll progress from like simpler to more complicated examples. First alkene I'll give you is this one. So this is one that's got the carbon-carbon double bond here. There's a carbon there and a carbon there. And if we break that bond right down the middle, pull the pieces apart in an ozonolysis reaction, the left carbon becomes a ketone. It becomes acetone. The right carbon of the double bond here becomes an aldehyde because it's got a bond to an H. You just have to make sure you don't lose any carbons in any of the groups that are attached to the double bond. But those are the two main products. The other product that you need to be aware of and not forget about is this dimethyl sulfide product. So sometimes questions will want you to show just the two carbonyl type products, and sometimes it'll want all of them, including this one. All right. Okay, not too bad, right? All right, let's put one into a ring, because this is another one that sometimes it's just a little different, and sometimes it causes confusion, but I'm going to help you figure it out. So imagine you had an alkene that was in a ring, and this ring is going to be a 6-membered ring that has a carbon-carbon double bond here, and I'm going to put a methyl group there. If you put this in with ozone in the first step, and then follow it up in the second step with sulfur with these two methyl groups, dimethyl sulfide, you imagine breaking that bond right there. And what you're going to do is pull these groups apart and put O's on them just like you did before, but the molecule, since they're tethered, they're not actually two separate molecules. They would look like this. I'm going to draw it in a way that maybe makes it easy to see, I hope. So they're still together, so they can't float away from each other. The carbonyls appear in one molecule because we had a ring and we broke it in one spot. But if you count, this carbonyl carbon here was one carbon of a 6-membered ring, and then it goes 1, 2, 3, 4, 5, 6. So these were bonded together. The aldehyde carbon was that carbon, and the ketone carbon was that carbon. Now you might see this drawn in a better conformation. This is not the most stable conformation or even a very good conformation. So you might see the product listed as something that's got a 1, 2, 3, 4, 5, 6, 7-membered chain. Let's draw that out. 1, 2, 3, 4, 5, 6, 7. This would be a better conformation to draw the molecule in. 1, 2, 3, 4, 5, 6, 7. And it came from a 6-membered ring where the 2 carbonyls used to be together as an alkene. This doesn't look anything like that, but this molecule is really just this, where it's adopted a more stable conformation. So these are just 2 different ways of drawing the same molecule. Okay. Sometimes you'll get questions that I want you to work in reverse. I'll show you one quick example of this. What if you were asked about this question? You wanted to say the molecule said, here's or the question said, here's a molecule. Figure out an alkene that when you put in ozone in the first step and dimethyl sulfide in the second step would give you this. So you got to think backwards with this one. And one thing you could do, if it's helpful, is you could imagine just rotating this thing into a conformation that makes it look more like a ring. Maybe this helps. 1, 2, 3, 4, 5. These groups used to be connected. So the product would be one where you've got that structure. Breaking that bond with ozone would give you that thing, where you've got the same number of carbons, the oxygens just take the place of the carbon-carbon double bond. So, it's going to require a little bit of thinking and a little bit of getting used to, but there's some good problems in the homework that will give you some practice. And when we come back on Friday, we're going to talk about alcohol oxidation, and then we'll do some review. So have a good day.